Hello everyone, I'm Kwon from KAIST, and my advisor is Myoungsoo Jung, who leads Computer Architecture and Memory Systems Laboratory. Today, I'll introduce our work, which is Vigil-KV hardware software co-designed to integrate strong latency determinism into log-structured merge key value stores. Let me explain about our target research domain. Our goal is to guarantee strong latency determinism. Here, latency means the read latency that determines user experience. By the way, why is read latency closely related to the user experience? Let's think about the web page loading scenario. If you cannot read the web page within your expected time, you would like to give only 1 star for the score. As a more practical number, Google reports that 1 second longer web page loading time loses 20–30% of users, and Amazon reports that 100 millisecond longer web page loading time loses 1% of revenue. Thus, this work aims to achieve strong latency determinism for reads without long tail latency. Let's zoom in on our target scenario with the Facebook workload. When the client executes the Facebook application, front-end tries to display the news feed to the client. For this, the front-end should access the backend database to read the relationship information and media such as images and videos. In this slide, I will break down the latency into front-end time and backend time. As shown in the right, the average newsfeed read latency is only 0.26 milliseconds. However, at some point, the client can suffer from 11 times longer read latency, which can worsen the user experience. By the way, why does the unexpected long latency occur? As shown in the graph, we can realize that the unexpected long tail latency comes from the backend database, not the front-end side. From now on, let's check what backend system looks like and what impacts long tail latency. Backend database usually adopts log-structured merge key value stores such as LogsDB. In the backend system, the user's read query is delayed by LSM KV's internal task. In the next slide, let's briefly go over the LSM KV's internal task. LSM KV consists of memory side and storage side data structures. In the memory side, there is a data structure called mem table, which can insert the key value pairs in an append-only manner. When the mem table is full, it is changed to a read-only data structure called immutable mem table, and it is flushed to storage in background. And the flushed mem table is managed as SST file. This mem table flush is the first LSM KV's internal task that we have to keep in mind. Disk side LSM KV adopts multi-level architecture, which is key value pair insert friendly. When level 0 is full, the corresponding SSD file moves to the next level, level 1. If LSM KV is getting filled with key value pairs, we cannot simply flush the mem table. We have to merge multiple SSD files across LSM 3 levels, such as level 0 and level 1. This SSD compaction is the last LSM KV's internal task that we also have to keep in mind. Then from now on, let's check the impact of LSM KV's internal task. By comparing them with a read-only performance, which is colored in orange in this graph. By the way, why does the read latency increase when we run the read and write operation, although the mem table absorbs all the write operations? In the storage side, there is one more data structure called write-ahead log. Before keeping a key value pair in the memory, we have to record the history into the var permanently. After that, we can insert that key value pair into the mem table. As all write operation generates our request for var, it can also interfere with the read request. When the number of puts increase, mem table flush will occur, As shown in graph, MEM table flush worsens the user's read latency as high as 3 milliseconds. Moreover, SSD file compaction also impacts users' read latency significantly. As a long tail latency comes from the interference of LSM KV's internal task, several studies try to service users' query as earlier as possible and reschedule or delay the LSM KV's internal task by leveraging the idle time. However, existing internal task scheduling or delaying the method is similar to patching the bump. Let's suppose that there is no user idle time and the MEM table flush keeps delaying. In this case, LSM KV's memory space is getting larger, but we can ensure the latency determinism for the user query. However, when LSM KV reaches to the maximum memory capacity, the bump blows up. In order to reclaim the memory capacity, all the MEM tables should be flushed to LSM tree, and it causes latency spikes for the user queries. Not only for the LSM KV's internal task, user query can be interfered with SSD internal task as well. This is the second root cause of long tail latency. If you look into the SSD's internal architecture, there is DRAM, which is used to hide the long write latency. The SSD flushes dirty data into the NAND flash in the background. As shown in graph, we can check the DRAM flush increases read latency almost 2 times. In addition to DRAM flush, SSD performs garbage collection in background to collect valid pages. As garbage collection reads and writes multiple pages, it interferes users' I/O a lot and increases the read latency almost 9 milliseconds. Moreover, SSD should perform the read reclaim for the read hop pages. When a page is read a lot, the voltage distribution is shifted to right. As it can reduce the software, cause software error, we have to rewrite that page. Read reclaim also interferes users' read recast and increases it up to 3 milliseconds. As a solution of SSD internal task handling is standard NVMe protocol, which is predictable latency mode interface. PLM interface allows 2 device states of underlying storage, such as deterministic window DTWIN and non-deterministic window NDWIN. SSD internal task only can be performed during NDWIN. That's why DTWIN can guarantee the deterministic latency to host. However, current PLM interface is just best effort contract, and there is no detailed guideline for this, which can make us hard to use it. Let's summarize what we went over until now. Rescheduling or delaying the LSM KV's internal task can reduce tail latency somewhat. However, it cannot fully eliminate the tail latency, and delayed internal task should be performed at some point. And handling SSD internal task with PLM interface is a good starting point to support hardware-level latency determinism. However, this is just best effort contract, and there is no real prototype. Moreover, in order to achieve the deterministic latency, we have to store both LSM KV's internal task and SSD's internal task. However, there is no solution for both of them at the same time. Thus, in this work, we propose Vigil-KV, which is designed with close collaboration between storage and host-side software. With Vigil-KV, we can achieve storage latency determinism, and it can reduce 3.2 times shorter tail latency compared to the state-of-the-art solution, and can reduce 34% of average latency as well. First, let's check the Vigil-KV hardware. Our Vigil-KV hardware supports two opportunities and 3 constraints. First of all, Vigil-KV hardware supports space division opportunity for Vigil-KV software by partitioning single device into multiple NVMe sets. Each NVMe set guarantees performance isolation at the hardware level. In addition to the space division opportunity, Vigil-KV hardware provides time division opportunity by enabling PLM interface per NVM set. With this time division opportunity, Vigil-KV hardware can be in two different performance windows. Vigil-KV hardware enters to DTWIN when user sends the set DTWIN comment, while it enters to DTWIN when set DTWIN comment arrives. Not only for the time division opportunity, but Vigil-KV hardware also reveals 3 PLM constraints that Vigil-KV software must know. The first constraint of PLM is write-free on DTWIN. Although Vigil-KV hardware enters the DTWIN performance window, if a user sends write request during DTWIN, Vigil-KV hardware automatically turns into DTWIN performance window. Thus, the write after reads cannot enjoy the deterministic latency of DTWIN. Thus, Vigil-KV software should consider this constraint and serve read requests only during DTWIN performance window. The second constraint of PLM is fair scheduling for PLM windows. Let's suppose our target application requires high query per second and wants to stay in DTWIN for a long time. However, Vigil-KV hardware can stay in DTWIN until it reaches to maximum DTWIN time, called max DTWIN. Then what about sending set DTWIN again right after DTWIN entrance? In fact, it does not work, since DTWIN should be stay in that state at least pre-configured minimum time called min DTWIN. Thus, Vigil-KV software should consider this constraint and do the device state scheduling. Note that DTWIN time can be shorter than the max DTWIN, while ending time can be larger than min DTWIN. The last constraint of PLM is device lockdown. Although we send set DTWIN command to Vigil-KV hardware, it does not turn into DTWIN immediately. After device lockdown time, Vigil-KV hardware sets to DTWIN and can serve user requests. With the 2 opportunities and 3 constraints the Vigil-KV hardware supports, let's design Vigil-KV software. Our Vigil-KV software performs data placement, device state scheduling, and request scheduling. First, let's talk about how Vigil-KV software places LSM KV data and metadata. By leveraging the Vigil-KV hardware space division opportunity, Vigil-KV software stores LSM KV's metadata into separated NVM set, while the remaining NVM sets are used for LSM KV's data, such as SSD files. We will call each NVM set as KV set and meta set. As metadata is isolated from key value data, LSM KV can perform the data logging whenever it wants. Also, LSM KV's data can be free from the metadata I/O interferences. Secondly, let's talk about how Vigil-KV software schedules the device states. The goal of Vigil-KV is to support the deterministic latency 24/7. However, based on the PLM's fair scheduling constraint, single NVM set cannot support the deterministic latency 24/7. To solve this PLM limitation, Vigil-KV software adopts array-level storage technology that can group multiple KV sets into single volume. When data comes, Vigil-KV software makes it as 2 chunks and calculates the parity of 2 chunks and store them across multiple KV sets. After that, if it schedules device state by considering other KV sets' device state, we can guarantee the deterministic latency 24/7. As shown in this slide, Vigil-KV software schedules the DTWIN state and most only 1 KV set. Thus, if the target KV set is in DTWIN, Vigil-KV software reconstructs data by referring other 2 KV sets data. However, this device state scheduling is not correctly working in PLM. We have to modify it. By considering the device lockdown constraint, we have to guarantee only 1 KV set is in DTWIN or device lockdown. At last, let's talk about how Vigil-KV software schedules I/O requests. Vigil-KV Software schedules LSM KV's I/O requests to NVMe while scheduling users' I/O requests to DTWIN for latency determinism. To give hint to the Vigil-KV software, we modify LSM KV by adding I/O priority to each client thread and internal task threads. Then now, let's implement Vigil-KV hardware and analyze its characteristics. Here, I summarize our Vigil-KV hardware specification. The total capacity of Vigil-KV hardware is 2 terabyte and totally it has 8 channels. Our Vigil-KV hardware currently supports 4 NVMe sets, which can manage the device state independently. As our NVMe sets have their own device state, the host can control Vigil-KV hardware in a fine-grained manner. Then let's implement Vigil-KV hardware step by step. The key idea of partitioning is minimizing hardware resource sharing. In this slide, I will assume Vigil-KV hardware only supports 2 NVMe sets for sake of brevity. The implementation of partitioning is not difficult. Each NVMe set separates physical functions, cores, on-chip memory, internal DRAM, and flash channels. Based on NVMe set ID, the activated hardware resources are different. That's why we can isolate both performance and device state per NVMe sets. Now you wonder the NVMe sets are isolated or not. In this slide, I will show you our hardware validation result. First, we group 2 NVMe sets in a single storage volume, and we co-run the read word code colored in blue and write word code colored in red. In the right side, gray color graph shows the read word code's latency. As shown in graph, the read latency exhibits the long tail latency as much as 2 milliseconds due to the write request interference. Now let's isolate the read word code and write word code. Read word code uses NVMe set 1, while write word code uses NVMe set 2. Then let's check the read latency behaviors with blue color graph. As shown in graph, there is no long tail latency and all reads experience similar latency. As we successfully implement multiple NVMe sets, let's integrate PLM interface per NVMe sets. Enabling PLM interface is also not difficult implementation. Each NVMe set has 2 request queues, such as legacy I queue and internal job queue. Legacy I/O queue manages I/O requests comes from host, while internal job queue only manages I/O requests comes from the SSD firmware. If device state is in DTWIN, I/O requests in legacy I/O queue are serviced. If device state is in NVMe, I/O requests in both legacy I/O queue and internal job queue are serviced. That's why NVMe does not guarantee the deterministic latency for host. From now on, I will reveal 3 PLM constraints or behavior based on our hardware prototype. Let's check from the first constraint. Our Vigil-KV hardware automatically turns into NVMe when there is a write request during DTWIN. However, if user ensures write-free on DTWIN, our Vigil-KV hardware guarantees read latency under 200 microseconds. Let's move on to the second constraint. As shown in this graph, we can observe fair scheduling of PLM windows. Specifically, the maximum DTWIN is 16 seconds and minimum NVMe is 4 seconds in our Vigil-KV hardware. To check the last constraint of PLM, we analyzed device lockdown times varying based on how data were written in the previous NVMe. And as shown in graph, it is sufficient for the host to hold the data by under 20 milliseconds. Here is the summary of rebuild PLM behaviors. When users want to use the PLM-enabled SSD, they have to consider these values for their device or request scheduling. Before I end my talk, I will show you the representative evaluation result. Compared to the state-of-the-art solution, our Vigil-KV reduces the long tail latency 3.2 times. Also, we can reduce the average read latency as much as 34%. The proposed Vigil-KV is a hardware and software co-design framework that eliminates long tail with strong latency determinism. We implement the world's first PLM interface prototype, also supports host-side software for PLM prototype. Furthermore, we reveal the PLM constraints that have never discussed before. Thank you for your listening, and if you have any questions, please ask me.